Hey, what's going on, internet? Today we're going to be talking about ARM assembly. We're going to be doing a little bit of coding, and by the end of this, you should be able to write a hello world in ARM assembly that will run on any VM that you have. So let's dive into it. So step one, right? What is assembly? Assembly is code that is one layer above machine code. So if you look at this example where you have a compiler that's you're writing C, you're putting it in GCC. GCC at first will actually put it into assembly language here, and then it will rely upon an assembler here to bring it to machine code, right? So if you write assembly, we're writing the instructions that our computer will run eventually, but in a human readable format. In this form, it is not consumable by the computer, but it will be at a certain point. We're not there yet at this point. So today, like I said before, we're going to go over the ARM architecture. It's a RISC architecture, so that's reduced instruction set compiler, which basically means it has very few instructions. It's meant to be simple and easy to work with. ARM in particular has become increasingly popular in embedded in IoT, so there's a pretty good chance that the router at your house is either ARM or MIPS, but mostly ARM if it's newer. And in my opinion, don't flame me for this, but I think ARM is way more consumable for the beginner over x86, Intel architecture. So ARM consists of a set of registers, right, like any other processor would. Registers are physical, hyper-fast memory that live inside of the processor, and the registers allow us to do quick math operations inside the processor. ARM is a byte addressable architecture, which means that you can ask it to pull memory from any address. It doesn't have to be 4-byte aligned like some architectures do, like MIPS. And then ARM operates in two modes. You have ARM mode, which is the mode where instructions are 4 bytes long, and every PC increment when you're executing increments the counter by 4. Or you have thumb mode on some processors where you increment by 2. This may be pretty deep for some people. If it is, don't worry about it. We're going to go into some basic assembly instructions, right? So ARM instructions are written in the format an operator, destination, source, operator, destination, immediate, and immediate means like a number, like 4 in this example. And if we get into memory operations, which again, not in this tutorial, but just to kind of put it out there, operator, destination, address. So look at this example, right? Really, really easy. Move, that's the operator. It says to move a value into the destination R0, the number 4, right? So at the end of this example, you're going to have the number 4 in register 0, right? Cool. I think this is pretty straightforward. I hope you guys are sticking with me. If I'm going too fast or whatever, leave a comment and let me know. But we're going to get into some coding right now. So pull up your computer, and step one, if you haven't already, please run this command. This is going to get you the ARM build chain for Intel, right? I'm assuming that you guys are working on an Intel VM, like a regular VM on your computer. Just go ahead and run that. I already have it. You'll walk through the steps. You'll hit yes, and you'll install your VM. Okay, so then over here on the left, we have our code. So go ahead and type this out in I use Vim, whatever, Emacs, if you're one of those people that you want to use. So let's walk through what we have here. This is the beginning template for anyone writing assembly using GCC's build chain, right? So pound, this is a comment, doesn't really matter what that says. Global start. So global start allows the variable start to be accessible outside of this file and makes it an exported symbol that the rest of the build chain can touch. If that's too complicated, don't worry about it. All it means is that this start symbol is accessible. All right, we need to have that start for this code to be compilable. Next, we have section text. Text is also referred to as code, right? So that means that anything south of this label is to be interpreted as code, right? And that makes sense because our start label, where the code will start, has to be in the text section. And then finally, section data, anything that is to be interpreted as data that is not executable will live in this region, right? Cool. So now that we have that all written out, let's write some code. Let's do some stuff. Let's try that instruction we had before, right? So pretty straightforward. We're going to do move R0, boom, comma, pound 4. The pound in ARM assembly means it's an immediate. So if you did 4 by itself, it would yell at you. You need to do pound 4. Cool. Okay, awesome. So the way that we first save, and the way that we compile this into an executable blob is by doing the following, right? So we need to run the assembler. So that's going to be ARM Linux GNU ABI, and then we're going to do AS. AS is the assembler. That is what's going to convert our machine code, this code over here, into, what turns our assembly over here into machine code. So the syntax for this is going to be ARM Linux GNU ABI assembler. We're going to consume what I called my 001.asm file, that's our source code, and we're going to output 001.o. Good, no errors, awesome. So what is the .o file? The .o file is a relocatable object. This is a intermediate object that GCC will later consume to produce an executable ELF, right? Again, if that's too complicated, don't worry about it. Not particularly important, just something to be aware of. Cool, so now we have our assembly converted to machine code, but it's not executable yet. We just need to run it through a final pass of the linker by calling GCC, and then we'll get it to run. So we're going to take the object file we created, and we're going to produce an ELF. Damn it. Oh, I forgot one critical piece. We have to say no standard lib. If we don't say no standard lib, what will happen is the compiler is trying to include libc in our program, and we don't want it to happen, because when you include libc, this start gets redefined, it tries to call main, we haven't called main, it's a whole mess. So no standard lib. Boom. So if we run a file on 001.elf, we should get a full, good-looking 32-bit least significant bit elf for ARM with the build hash, not stripped, all that good stuff. And then to run it, if you haven't already, sudo apt install QEMU. I already have it, so I'm good. And the way you run this in a non-ARM, build environment is QEMU ARM our elf. Interesting. So we got a crash. Why did we get a crash? The reason we got a crash is that the program went to run this instruction and then everything else that's beneath it. Now it may look like there's nothing beneath it, but there is actually. If you look at the elf file, our instructions live somewhere in here, this number 4, right? It tried to execute all this crap beneath it, and the reason is we didn't tell the program to properly exit. So you may be asking, right? How do you make a program exit in ARM assembly? Well, that's where the system call comes into play. We'll talk about that right now. So, what is a system call? When you're doing programming in user mode, which is what's happening when you're writing assembly, right? You're writing a user application. You need to eventually ask the kernel for help, because the processor or the user mode process cannot end its own process. So we call this thing called a software interrupt to ask the kernel to take some kind of action, right? And in ARM architecture, R7, register 7, the value that is stored there determines what we do. That's called the system call number. And then R0 through R4 determines how we perform that action, right? So for example, like we were talking about before, we wanted to perform an exit. Okay, how do we perform an exit using this? Well, what we're going to do is we're going to go back into our coding environment, and we're going to Google. I already have it pulled up, but to show you guys how to get here, right? ARM32 system call table. And then luckily Chromium OS has documented this for us. You can find a whole bunch of these everywhere. But you have this system call table for Linux, and you're going to want to go to the ARM 32-bit version. So we have all of the services the kernel is able to offer our program, right? So for this case, we want to run the exit system call. How do we do that? Well, we put the number 1 into R7, the error code we want to return. So our process will return this value into R0, and then we call the software interrupt instruction. So let's do that. So we said R7 had to have, sorry, what did I say? R7 should have 1? Yes, R7 should have 1. And then in this case, let's just return, I don't know, let's return 13. So this notation up here is hexadecimal, this is decimal. And then we do software interrupt 0. We recompile our program, so we assemble using AS, our assembly into machine code. Then we compile into an ELF using GCC, and then we try to run it. Awesome. So we ran the program, it didn't crash, and what was the return value? 13, perfectly, right? So the program worked exactly as we expected. Cool, so well, what have we done? We've written some ARM assembly that did something we expected it to, and then it didn't crash. Well, I promise you guys at the end of this, we'll be able to write a hello world. So I'm gonna satisfy that promise. There are a few more things we have to do first. So how do you write to the screen? Okay, we did an exit before. What is the write process? Okay, well, I said that the kernel probably has to take care of this using some kind of kernel service. Oh, well, there's a write. Okay, how do we write to the screen? In Linux, there are three file descriptors by default. There's standard in, which is file descriptor 0, standard out, which is file descriptor 1, and standard error, file descriptor 2. So what we're going to end up doing is we are going to write a string to the standard out file descriptor. Okay, and how do we do that? Well, let's ask the system call table. We need to set R7 to 4. We need to set R0 to the file descriptor we're going to write to, which is 1. We're going to set R1 to the data we're going to write to the screen, and then R2 to the length of that data. We're adding a few more arguments now, so instead of just the R0 before, we have R0, R1, and R2. A little more complicated, really not that bad. All right, so what do we say we're going to do? The system call is now system call 4. R0 is now the file descriptor 1. We have to set R1 to something, right? Okay, what is that something? The something is the data we're going to output to the screen. Let's define that data in the data section. That makes a lot of sense, right? The message, so this is a label. We're calling the message we're going to write message, and it is of type ASCII, and it's hello world with a new line at the end. Cool. So what does that do? We've told the assembler, hey, in your data section, there is an ASCII string of this value that we're going to refer to as message. We're going to introduce a new instruction called load register. And what this is doing is when you're dealing with memory operations, and because we're loading the memory address of a location, we have to use this syntax. So we're saying load into register 1 the address of the message label. Pretty cool, right? And then finally we move into R2, the length of the string. So how long is this? We have 5, 10, 11, 12, 13. And then invoke the interrupt. Okay, great. Interesting. So we assembled our assembly into machine code. We compiled it to a runnable ELF. We ran the ELF and we got our data, but we got a crash. Why is that? Same problem as before. We failed to exit. So we're going to rewrite the exit shellcode. And we'll return 65. 65 is a very funny number in the embedded world. We'll get into that in a different video. Save our code. Reassemble. Hello world, prints a new line, no crash. There you go, guys. I hope you had fun here. I hope you learned something. If you did, drop a comment. Give me an idea what you want to learn in the next video. Thanks for watching, and keep learning. Thanks.